Okay, AP Calculus 8 BC, Unit 4, Day 1, brand new unit. Let's study polar coordinate system. So it's another way of describing the location of a point in an XY plane, two-dimensional plane. I'm trying to get this camera fixed, but I don't know. Come on. Okay. So this is just the first day. We're going to kind of figure out what it's about, start to do some graphs with it. So what you're used to is rectangular coordinates, where you describe a point. Say this point would be 3, 2, and it's an x and a y coordinate, and it lines up with the x value 3 on the x-axis and 2 on the y-axis, and it gives you the location of the point. So it's directions for finding a point. So this point would be 3, 2, parentheses x first, y second. But we could also describe this with some other values. And so the origin, what we usually call the origin, the beginning, is called the pole often in this situation. And the x-axis is called the initial ray. And what we do is we use an angle and a radius to describe the same point that we're just looking at just now. So the radius would be the length of the line connecting it to the origin or the pole. And then, so that's going to be r. And then we're going to figure out what the angle is, starting at the positive x-axis, which is what we're used to anyways with angles. So usually when we think of angles on an axis like this, we think of them starting on the positive x-axis. So to get this, we could do a little Pythagorean theorem. We could use the x and y coordinates that we already know to help us figure out what the values would be. So this would be 2 squared plus 3 squared. So it'd be 4 plus 9 is 13. You take the square root. It's going to be positive because the radius has to be, well, in general, distance is positive. We'll actually talk about negative radius. So that would give you the radius, which is always going to be the first coordinate. Like x is always first coordinate. It might take a little while to get used to. And then the angle. Now, the angle needs to be in radians, which I think we're used to now in calculus, that we're generally working in radians instead of degrees. So we could use, there's a little right triangle that gets created here, and we could do any of the basic trig equations, sine, cosine, or tangent. I'm going to use tangent because opposite would be 2 over adjacent would be 3. So opposites across from, which is the y value, 2 over adjacent's the x value. And then we could use a calculator if it wasn't a common angle, and take the inverse tangent of both sides. And the calculator would give you 33.690 degrees or 0.588 radians. Now, usually we don't put the little r for radians, but you could if you want. So this should be 0.588. So this is the same, describing the same location in the plane as that xy coordinate, 3, 2. Now, be careful with your calculator. Your calculator in general gives you principal values. So for sine and cosine and all those, for anything positive, in this case, it's always going to be quadrant 1 for sure. So sometimes you're going to need to figure that out because you might not be in the first quadrant. Now, in this particular problem, we were in the first quadrant, so it made sense. So let's look at some other just kind of examples here. This is a famous polar function. So now we're going to actually start to write functions as r in terms of theta instead of y in terms of x. And what we're going to do, I think, a lot at the beginning and even in the future is maybe just make a quick table and write some values down. So if you plug 0, and this is very simple. This is like y equals x, r equals theta. Y equals x gives you a straight line at a 45-degree angle through the origin, but this is not going to give you a straight line. So these often give us very curvy kind of shapes. Doesn't have to. If you plug 0 in, you get 0. You plug pi over 2 in, you get pi over 2, which, by the way, is about 3.14 divided by 2 is about 1.57. So we're still graphing these on an xy coordinate plane. It's kind of interesting. So 0, 0 would be right here. So you're at the angle 0, and you have a radius of 0. So you're 0 away. So you're at what we call the pole. And that's where the graph starts in this case right here. So we're just doing positive thetas. We'll look at negative thetas in a second. And then pi over 2, well, pi over 2 angle is right up here. That's like a 90-degree angle, right? This is 2 pi. So pi over 2 here, and then we're going up 1.57, which is like right around there. And then at pi, we're going to be at pi, which is 3.14. So pi would be all the way over here, and then we're facing the left. Okay. And 3 pi over 2, well, it's going to give you 3 pi over 2 as an estimate. It would be 3 of these, so like, I don't know, 4.71. So 3 pi over 2 is going to be all the way down here. And now you're now at 1, 2, 3, 4.7. And then at 2 pi, you're at 2 pi, which is about 6.28. So that's going to be like right here. Now what's happening is if we keep going, it's going to keep getting bigger and bigger. It's this kind of spiral looking shape. Like you could find more values in between, but this is what's happening, and it's just gonna keep going, right? It's gonna just keep going. And then so that's they call Archimedes spiral. Now, if we did the negative case, theta is less than 0. I'll do that with like a light line. You get the same value, 0, 0. So it starts here. Now, by the way, there's a direction to these. So it starts there. So kind of like parametrics. We have a direction. We have an initial point potentially and a terminal point potentially. So it's going around like this. If you did the negatives, you get 0, 0. And then you'd be at negative pi over 2, which is going to be backwards, but then you get a negative radius, which flips it up. So you can actually have, so positive radius is going to be in the direction of the terminal side of the ray. It's going to go in that, but it doesn't have anything to do with x or y being a negative radius. Means that whatever angle is pointing to, a negative radius is going to flip it backwards. So even though we're going to be at negative pi over 2 and we're going to have a negative radius, it's going to flip it up here. And then we're at negative pi, we're here, but so we're facing this way, but it has a negative radius, so it ends up over here. So what happens is, I'm going to just do this lightly, you get, oops, I messed up. You get this kind of graph. Kind of looks like a mirror image of the first one across the y-axis. So we'll talk about negative radius more, but that's something to kind of get used to. What negative radius means it's going to go backwards from the direction that the angle is pointing to. Now, conversions, we already kind of talked about this a little bit, but we'll write this kind of more generically for any x, y. Rectangular coordinate pair, we're going to use Pythagorean theorem because you get a little right triangle. And so it's going to be r squared equals x squared plus y squared. And so then r is going to equal the square root of x squared plus y squared. And we're going to generally say right now that, okay, it's going to be positive, at least from Pythagorean theorem's point of view. And then the angle, we're going to use any of the basic trig functions, sine, cosine, or tangent. I like to use tangent because it uses the two values that you have. So opposite over adjacent is going to be y over x. And so theta is going to equal the inverse tangent of y over x. Now remember, calculator gives you principal values, so you're going to have to, for tangent, that's always quadrant 1 and 4. Quadrant 1 for the positive version. Now to go the other way, if you have r and theta to begin with, could you get x and y from that? Could you get the rectangular coordinates? And so we're going to use basic trig So let's say you have r and theta and you want to find x, well, you'd be like, well, that's adjacent over hypotenuse. Let's use cosine. Cosine of theta equals x over r, and so then x equals r cosine theta. It's a pretty simple thing. Like you don't have to memorize. I mean, you're going to probably use these enough to start to memorize them, but it doesn't. It doesn't have to. It's a really simple kind of relationship that you can always just kind of reimagine. If you want the y value, that's the opposite side from the angle. This angle is always at the origin here. So that's the opposite of adjacent. So you don't want to use sine equals y over r, and so then y equals r sine theta. So they have very similar relationships. So one's cosine, one's sine. You got to keep those straight. Cosine is, think uses adjacent side, which is always on the bottom, is it's always left, right, horizontal. So we could try and just do a couple conversion examples. Now, what you could do at first to help you is draw a picture. So you could say, okay, well, this is r and this is theta. That's one thing you got to remember, is that r comes first and theta comes second. You probably don't have to think very hard with regular rectangular coordinates. You're probably pretty good at thinking x is first. Alphabetically it makes sense, I guess. Here alphabetically it makes sense too. R before theta with a t, th. Maybe that helps. Okay, so we could just kind of roughly graph this. Pi over 3, this is pi over here, right? So pi over 3 would be 1/3 of that. So that's the angle. And so pi over 3. And then the radius is 6. So we're trying to figure out that point right there. So what we could do is draw a little right triangle. And this is the x coordinate, right? And this is the y coordinate. And in this case, we could say, oh, this is a 30, 60, 90 triangle, right? And so if the hypotenuse is 6, then the short leg is going to be half of that, and then the long leg is going to be the short leg times root 3. And so your answer is going to be 3 comma 3 root 3 without a calculator. And then or you could just kind of calculate it from these formulas that we wrote down, which I think you're going to get to a point where you're going to start to remember very quickly. Oh yeah, r equals cosine theta. So if r is 6 and theta is pi over 3, you say, okay, what's cosine of pi over 3? Well, it's pi over 6, pi over 4, pi over 3, pi over 2. So it's that later angle, 1, root 3 of 2, root 2 of 2, 1/2, right? And so you get your x value that way. And then the y value would be r sine theta. I'd recommend writing these formulas down as you're using them because it'll help you remember them. And so sine of pi over 3, well, that's, like I said, 0, pi over 6, pi over 4, pi over 3, pi over 2. So 0, 1/2 root 2 of 2, root 3 over 2, which give you 3 root 3, and that's your y. And so then that's your answer. So it's probably a little faster, and you don't have to draw the picture every time. But the picture, at least at first, as you're trying to get the hang of this, it's kind of helpful. So in the back, I have another one. You guys could try it, pause the video and try it out. So like I said, you could remember, okay, well, x is going to equal r cosine theta and y equals r sine theta. So we could just jump right into that. It's going to be 12 cosine pi over 4, comma 12 sine pi over 4. I mean, there it is. I mean, probably want to simplify it. It's going to be root 2 over 2. So it's going to be 6 root 2. And that one's going to be 6 root 2. So a little faster than drawing a picture. Next one, we could do that. We could say, okay, well, 6 cosine 5 pi over 3. 6 sine 5 pi over 3. So Now this one's a little trickier because this is quadrant 4, I think, right? And the reference angle is pi over 3. So that's going to be cosine of pi over 3, 0, pi over 6, pi over 4. It's going to be 1 root 3 over 2, root 2 over 2, 1 half. And it's positive in the fourth quadrant for cosine. And sine is going to be root 3 over 2, but it's going to be negative. So we're going to get 3 comma negative 3 root 3. Which, by the way, does that give you a point that's in the fourth quadrant? Yes. So it should make sense, even thinking what quadrant is based off the xy pairs. Now, let's talk about the negative radius idea a little more. So direction is opposite the terminal side. Okay, so in this case right here, 5 pi over 4, this would be 0 pi over 4, 2 pi over 3, 4, 5 pi over 4. We always start at the positive x-axis. That's the beginning of it. Okay, so, and then the radius is negative 2. So you might think, oh, let's go right here. Nope, it's going to go backwards 2. And so this is your final answer for this polar coordinate pair. It goes backwards from where the angle ends. Okay, now we could describe this point. This isn't something that we can do with rectangular coordinates. We can actually write lots of different r theta combinations to give you the same point. I mean, this is the same thing as saying 2 comma pi over 4, right? Wouldn't that be at the same place? Pi over 4 with a positive radius of 2. We could go backwards. We could go this way. We could say 2 comma negative 5 pi over 4. That would put you at the same place. We could put we could go backwards here, say we could do negative 2 negative 3 pi over 4. That would give you the same thing. So there's actually infinite coterminal angles for sure. But I mean, I just wrote this in 4 different very kind of distinct ways, but there's, it could keep going. So this point right here, by the way, this is negative 2 pi over 4. That's a way to describe this point. So pi over 4 would be heading in that direction, but negative would flip it backwards. So, okay. So, here's some other problems where we could, kind of explore that idea a little more. This is the XY pair. So that would be, just roughly, if we were to draw it, 1 negative root 3 might be like there, right? So how could, and by the way, these are nice values that give us a nice triangle, so we don't have to use a calculator. So this is a 30, 60, 90 triangle, right? 30, 60, this would be 2. So, the rate, or we could do, you say the radius is 2, you could use Pythagorean theorem, 1 squared plus negative root 3 squared. So the negatives are going to go away when you calculate the radius. Or you could use 30, 60, 90. So the radius is 2, right? And then the angle, we've already said that's 60. So you could do this. You could say 300, or you could use that equation I gave you guys earlier. That tangent equals opposite of adjacent. So we could do, now here that the negatives actually do make a difference. So this is, if we're trying to do this without a calculator, say, oh, this is sine over cosine. Oh yeah, okay. What's the reference angle? When does sine equal root 3 over 2 and cosine equal 1/2 at the same time? Ignore the negative. You'd say, oh, well, that's pi over 3, right? Or 60 degrees if you want to say that. And then what quadrants could one be positive, one be negative? So that's quadrant 2 and quadrant 4, right? Now, it's not either one, because I mean, look at the picture. We know this is for sure quadrant 4. So there's not going to be two different answers here. It's got to be quadrant 4. And so in that case, theta equals, 300 degrees or 5 pi over 3. So the answer, I mean, some different ways we could write it. We could say, well, the radius is 2 and the angle is 5 pi over 3. Or we could say, let's go up here and then use a negative radius. So let's go to 2 pi over 3 and use a negative radius. That would put you at the same spot. Or, I mean, there's so many different possibilities. We could say, we could do negative pi over 3 with a positive radius, right? So just got to get used to that. Now, we're going to be doing a lot more of what's here on future assignments. On today's assignment, you're going to be sketching some of these. I want you on today's assignment to probably go and skip the last 2 problems because we'll get more into that tomorrow. I mean, you could try. And so you can check these on your calculator because your calculator has polar mode on it. So I'll show you in a second. Let's try it without a calculator first, though. Now, these are actually some really common shapes. But what I'm going to say first is let's just go ahead and just make a quick little table where we plug some thetas in, 0 to 2 pi. Let's plug some values in between, like pi, maybe pi over 2, 3 pi over 2. Now, if you plug 0 in here, cosine 0 is 1, plus 1 is 2, cosine of pi over 2 is 0, so that's going to be 1, cosine of pi is negative 1, so it's going to be 0, cosine of 3 pi over 2 is 0, that's going to be 1, and you're back to here. Now, if we were to graph these, I'm going to try and make my graph, I think, a little bigger to fit, make the graph a little nicer. So I'm going to make each value 2 hash marks. So 0 means the angle is facing the right and the radius is 2. Pi over 2 we're facing up and the radius is 1. At pi we're facing left, but the radius is 0, so you're at the origin. 3 pi over 2 you're facing down with a positive 1 radius, puts it down. And then 2 pi we're back here. Now what's going on in between these? These are usually very kind of curvy shapes. So we could throw another angle in there. Let's do, say, pi over 3. So pi over 3, cosine of pi over 3 is, that's 1/2, right? So that would be, let's see, and I'm going to also do 2 pi over 3. So both of these, reference angle is pi over 3, and it's 1/2. So this would be 1 plus 1.5 would be 1.5. So at pi over 3, which is kind of like here, we're at 1.5. So maybe like there. And then at 2 pi over 3, we're at cosine's negative 1/2. So it's going to be 1 plus negative 1/2 is positive 1/2. So at 2 pi over 3, we're kind of like right around here. And it's 1/2, which, remember, 2 of my marks equal 1. So that's like right here. So you're going to start to see this. This is what these look like. And we're going to get good at graphing these. So I'm going to get picky about wanting to look nice. But they kind of look like this. And they kind of round, almost makes you think of like a tomato or an apple. They actually have a special name. They're called cardioids. So it's kind of interesting. It's called a cardioid. And cardi is the, prefix for, or I don't know. Anything involving hearts is usually, right? Cardiac. So it's, I guess it looks kind of like a heart, not like your typical heart that looks like this, but I don't think real human hearts are pointy at the bottom anyways. They're probably a little more round anyways, and they got like so I don't know. So it's cardioid. And they actually, they create, there's some interesting applications of this. They create these cardioid microphones, and the cardioid is sort of the pattern, the pickup pattern. And so the the microphone picks up more behind it and less on the other side. So for recording live events, it's a good microphone because there might be lots of noise over here from the crowd, but you want to pick up the sound from on this side of it. So they designed them to have those kind of pickup patterns. And so here's one more. And so in tonight's homework, this is kind of the approach I want you to take. Now, to check your answer, you would go to mode, and we're usually not going to use this like on tests and stuff, but for right now, you could go to polar, POL, and then you go to y, and it has these equations. And so you could type it in, y plus cosine, and when you hit the X button, it gives you a theta. Kind of interesting. Now you want to go to window, and you got to put in the theta value. So 0 to 2 pi, and then you got to put X and Y values like normal. Now our graph, I'm going to estimate, maybe -2 to +3 in the X direction seems good, and maybe -2 to +2 in the Y direction based off our sketch and the values we got from the table. And so we could sketch it, and there you go. There's your cardioid. And it does kind of have a cusp kind of right there. And this kind of shape, we wouldn't be able to write a Cartesian equation for anyways. So it's kind of interesting. We are going to see shapes that we've done before with Cartesian equations, and we're going to figure out how to do them with polar functions. So let's try the next one. Just make a table, and 0 to 2 pi is pretty common. If you didn't do 0 to 2 pi, you probably won't get the full shape a lot of times. So 0 to 2 pi often will give you the full shape. And, sine 0 is 0, 1, 0, -1, 0. We might do some more in between. But I'm going to show you something else kind of interesting with this one in a second too. So 0, 0 would be right here. Pi over 2, 1. So I'm going to actually make, I think, 4 of these marks worth 1. Okay, and so 0, 0 is here. Pi over 2, 1 is right here. Pi is facing here is 0. 3 pi over 2 is down, but it has a negative radius, so it ends up here. And then 2 pi back here. So we end up getting these same 2 points a couple times. So it might be interesting to pick a point kind of in between. That's easy. Like pi over 6 gives you a nice answer for sine. It's 1/2. Now pi over 6 would be kind of like right here. That'd be 1/2. So I guess that would be kind of like, like right around there, I think. And if you did 5 pi over 6, that would give you also 1/2. And so 5 pi over 6 would be kind of over here, and 1/2. What happens is this shape is actually a perfect circle. And what happens is it actually gets graphed over the top of itself again. So you really only need 0 to pi to graph the full circle. And then it just, on any of these shapes, if you keep going, they're going to start to trace over themselves again and again. Now, here's an interesting thing. Like, could we convert this to a Cartesian equation? We know, you guys could tell, so by the way, it starts here. It has a direction. So it starts at the pole, and it has a direction. It goes like this. So we know what the equation of this looks like. It'd be it looks like a circle with a radius of 1/2, right? Because the diameter is 1, and it's been shifted up. It looks like half, so it'd be x squared plus y minus 1/2 squared equals 1/2 squared. This is the Cartesian equation that we would write for this perfect circle if I gave it to you and asked you to write it in some previous math class. Now, how can we get from this to this? And so I think we did some of this kind of stuff with, parametrics and converting them to Cartesian equations. So there's these formulas, these equations I showed you guys on the front. So x equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared. And we use these a lot. And in this case right here, r equals sine theta, right? So r squared would equal sine, would equal r times, I mean, you could say it equals sine squared, but we could also say that it equals r times r. And so it would be r times sine theta, which you'll notice is your y value. Okay. So if we take this equation right here and we say, okay, well, hey, this is the same thing as y, right? And so we could say, okay, well, x squared plus y squared, we're trying to get this equation. And if we have r, then that should work. And so what I've just done is I've replaced r squared with y, right? Because r squared equals r times r, and r, let me see if I did this right. Yeah, r times r, which could also be r times sine theta, and r sine theta is y. So then what we would do to get this equation to look like that, I mean, this is a Cartesian equation, but it's not really written the way that we're used to, is we move this over here and we would we'd complete the square. Negative 1/2 squared, and you would add the same thing to both sides. And we get y minus 1/2 squared equals 1/4. And what do you know? We've got the same equation. That's kind of cool. Anyways, in general, just to start to kind of talk about this, anytime you have a polar function that's r equals sine theta or r equals cosine theta, those are going to be circles. Now, the sine ones are always, and for all these shapes, by the way, the sine ones are always going to have a vertical kind of orientation, whereas any equation involving cosine is going to kind of have a horizontal orientation, which is kind of helpful. They could have like a radius in front, and that'll make them bigger or smaller. Also, another circle could just be r equals k. That would just give you a circle centered at the origin. It's pretty boring, boring polar function. But anyways, try the worksheet tonight. You can wait to do the last two problems, 12 and 13, because those, I mean, you could try them, but I'm going to show you, we're going to spend a little more time tomorrow trying to figure out how to graph those. They're kind of interesting graphs. All right.